Have I spoiled everything or all is okay? Everything. It will dry out in a short while. And then I will be able to remove these patches so that it will cover. Someone asked me that since it is bringing green on the sponge, isn't it getting spoiled? I hope I'm not spoiling. But I've used it before, so today is which day? Anyone who has fooled me before I go? It is done. Maybe the circuits. So I'll be a bit speedy and maybe today, not today. By the time we finish this section, all practicals will be done. All practicals we are doing, the theory will be done and you won't be having any theory to disturb you. Now, company, what is the problem? So we start with the characteristics of digital circuits. Supposed to be having a nice they are non-linear. They are non-linear. Did I say circuits or circuit? Let's start with the digital circuit. So it's non-linear. Then its signals take on only a particular or what we can call defined values. Okay, I've already given you the idea about digital circuits and why they are called digital, and they are non-linear, so you cannot say I'm going to get 1, 2, 3, 4, 5. This one is just binary, it's a 1 or 0. And if you have been keen, most of the advertisements of like digital brochures or flyers, you see many numbers, 10, 10, 10 written everywhere. Everything you deal with in a digital, these phones and the like, everything at the back is having 1 0, a high and a low, high and low, high and low. So they are not linear. You keep having a high, low, high, low, high, low, or 1 0, 1 0. It's not like if you are trying to measure pressure whereby you get these many pascals or newtons per, whether it's force over area, newtons is meters squared. What are the advantages of digital circuits? Advantages of digital circuits. Or since there are circuits giving us signals, let's take them as digital signals. These are too much, or you are fine? You have to see what I write. Analog. I saw a board which looked like this, but was a smartphone. So the guy just writes with his finger, he can zoom out, zoom in. And he was very proud that he can push it a little bit in the center. I loved it, but I want to promise you the chalk one. So what are the advantages of a digital signal, for example? What are the advantages of the signals? I mean, the signal you get here, whether it is audio, video, what do you find as an advantage of the signals you get? I see people say, yeah, we shall meet later on, then send the voice note. Now waits for theirs, then this says, okay, we shall meet. I don't record my voices to send, because now, in those days they used to say, they recorded my voice, now we record them ourselves and send the voice notes. I don't. People send, I write. How do you take my voice? They take it to somewhere. This didn't take a screenshot of my my voice. What is the advantage of the signals you have in your voice?
Imagine that there is less noise, less
less noise. What else? What are the advantages of women? A women.
Yes.
Or you want me to say a women? A women. What do you find so nice with the audio you get on your phone?
We have precision in action.
What? You are just getting you are listening to the radio, or they have sent you a voice note, or you are watching a video. What do you mean by precision in an audio signal that you are getting on your phone? How do you measure precision?
Like clear, clarity, it's clear without noises, as you say.
That he has already said about that. Try to tell me. I want to see whether you able to, and also to see whether you normally read or listen to me before I come. Sema.
Yes, I'm going to try.
Yeah?
Give it a try.
It's okay. Everyone is trying.
Digital signals, I don't know if it's the right word to use, the right synchronous.
Depending on whether you explain your asynchronous. There are two words which sound all seem to be the same. There is synchronous and asynchronous. But I can explain you, then maybe you choose which one you are talking about. Synchronous is like you can watch, if it is a video, you can watch it on your own. Let's say if I send you a video call, if I send you a video to watch, let's say I'm remote, I'm home, I couldn't make it, and then I send you a video to watch. That would be synchronous. Asynchronous means that we have, I don't know whether I'm saying the right thing. Asynchronous could be when you have to be live. Like you all have to listen to me at the same time. Let's say we have a telephone conferencing or a video conferencing, so that we all have to be online at the same time. So like a TV show is, I think is asynchronous, because we are all listening to the TV show at the same time. So which one did you want to mean? The one hour. Okay. But can't they also be this kind? Agaton, you got something?
What I was saying, probably to have a remembering, is like when we're talking about asynchronous, we're talking about something that is, the receiver says something as the sender also says something. For example, a phone call. You want to call, and I'm saying something and reply at every time. And then synchronous, for example, a TV show, we are presenting and we are here watching them.
So we can't participate. So this one, that's why I was very careful that asynchronous is when you are all participating. But synchronous, yes, you are all watching the stuff or listening to the stuff, but you are not participating. You are not in the thing. Yes, Mugara.
So I'm thinking about how is that going to be because both of them.
I first wanted to know what he meant, and he meant this. And if he meant this, the advantage is that it is easy for you to send a video nowadays. People just, you see them doing like this, and you know, I can come later. Let me send. Yes, I will.
Maybe I told you something that you had introduced recently, that you send a voice note and I transcribe it into text without listening to it. So maybe I can say to see this.
Like you are in a loud place, you are on a barrio, and then people, you don't want to know what they have said, so you transcribe it to read it as people are. But why wouldn't I have my headphone and listen? I don't know. Yes, sir. Very good. You are using a very complicated word, analyzed, but we can actually make it more manipulated. We can make it acceptable by everybody. Even the poor people in the slum can manipulate things. If you say they analyze, they feel intimidated. You can manipulate these days. Yesterday I took time off and said, let me go through TikTok and see what is going on. I think I support Mubaje. It should be closed. Okay, let me first hear from Bonnie. You can store a bunch of stuff because it is just 10101010. No big problem. But also there isn't storage. So it's talking about storage. I move with these cards. These cards, they are, I don't know how many they are, but they could be 10 maybe. And most of them are 32, and 2 of them are 64 GB. They are just here with me. Yes.
Is it fair to say that, let's say, analog signals are physical?
More or less.
Yes.
More or less. Because you have that magnetic tape, started with a Panasonic camera, which was using tapes. So you put in a tape and then you download. And then to download, I think it was very huge if you wanted good quality. If you wanted an HD format, one small tape was very huge. The size was huge. If you want to transfer quality.
So I think that my advantage.
Yeah, give me.
My advantage was it is easier to change from one format to another.
So easy to transform. The reason I'm giving you a chance is that the more you bring answers, the more you remember. Because you're the one who have... earlier there was a hand somewhere that I sabotaged. Yes, what? Over long distance. Transfer, you see, we get signals from satellites these days when we are using satellite TV, and it's not nearby. I think it is the nearest satellite is about 3,600. Is it 3,600 kilometers or meters? Kilometers. So and we get clear stuff. These days you can even just get a little bit of metal, add it on your antenna, okay, antenna cable, and then you still get a nice free-to-air signal. Very nice. And all that has been transferred to a long distance because of being a digital signal. So one thing that you have not told me that
in terms of energy use, you actually analog signal are a lot more energy intensive.
okay, of course, and if you are using, for example, video cassette or an audio cassette, most of the energy is in making sure that the tape turns. That's why the batteries just get finished. If you could get something else to move the tape, and the magnetic thing is being read, you wouldn't spend any energy. So they consume less energy. You just insert an SD card in the subwoofer and you start dancing around. No movable parts. But to get, and you find that like a 16 GB card can have a bunch of playlists, both video and yes, that. By the way, congratulations for finishing the, because now you have a smile all along. Before you didn't want to smile, whether there are rules of the fasting or the hunger was always giving you trouble. Because one of the students who were presenting their work in third year were applying for breaking the fast because we were getting past 7, so they were really not having any energy. But you make your point. There is? Okay, reduced interference. What do you mean by interference? Simple terms. What do you mean by interference? Security goes by replacement. Well, this was the storage in terms of capacity.
Yeah, but there is also an unauthorized
just put it there, and someone will come, and once they can access it, they will play the music. But I can put a password on my file. Whether it is a Word document, whether it is a PDF, I can put a password. You get to go to my email, you find my file, but it is encrypted because of being digital. But unless if you put these papers in the briefcase and lock the briefcase, so we are looking at an analog. This is my analog file of notes compared to my notes which are on Mwere. If you don't have an account and a password to access and an enrollment key to access Mwere, you can't access all my file. But now here, if you manage to break into my house and they are not in a safe or in a briefcase, I'm doomed. Yes, Miguel. Accurate. I'm just looking at whether you have said so. The flexibility will fall here, but then the idea is this is more important. Accuracy. That's why I can either be off. I'm sorry, this is not good, but I have to do it. I'm either off or on. I cannot be in the middle or in the 3/4 or a quarter. I have to be specific. And you have not given me one last point, which I want to hear. Daniel, what do you know about digital signals? Yes, Irunji.
High-speed transmission.
Huh?
High-speed transmission.
High-speed transmission. Yeah, let's because this one saying we can transfer them for long distances, and that's because they are speedy. And when you reach electromagnetism next year, this is the end of your second year. So next year you'll be able to find out that electromagnetic waves can move at the speed of light. And this was the advantage Marconi used to do transcontinental communication using a radio. So we will do this for that. Lastly, Elvis, say something. You can't sit in front here, get filtered knowledge, and just be there. You don't want to try. Okay. I respect your job. Anything about digital stuff, if you believe in digital stuff, since you are a very strong guy. So simple. Yeah. Minus 5 marks. Okay, well, the point I wanted to say still fits here. I don't know how much it fits there, but they can be regenerated. Regenerated. They can be regenerated. Of course, if you have, if you are doing stuff and things go wrong, you know you can do undo. Just giving a simple example, just to get you are adding something and it jams, you have undo. If you are writing on this piece of paper with a pen or drawing with a pen like you want to do, when I'm begging you to use a pencil, you cannot redo. You just have to cancel or be that try to change an A into an E, then you start doing like this. But with the digital, you just delete. You get that, so we have regeneration, we can regenerate. And then the repeatability. You just take one clip, and then you can, the way karaoke people do, you can have a chorus of just one clip. If there's one song I like some time back, so I only had to pick what I like in that song and make sure that I repeat it so it becomes a big song, but below that part. There are these songs where you find that there is a part which you like. The tone is nice, the words there are good, so you just pick that and you throw away the other thing. And if you want, you can always again back, bring them and fit them. And so that's what we mean by regeneration. So by the end of this course, you'll be a DJ of your own, that you can play around with your audio stuff and then change it, make it better the way you want.
Yes, so that regeneration includes copying, replication.
Yeah, copy paste. And when you paste, it's the same stuff.
And you can see the same things again.
When I'm editing my videos and you have chopped pieces and this piece is also important, so you find that you keep repeating them. If these videos I was showing you about remember when I was trying to explain the horse, and then I told you of the road videos whereby you can easily see the expressway, things going forward. Then you can, there is a song in the background. That song is repeated by copying the parts that do not bore the listener so that they are repetitive. So you are able to copy and paste as you have. So the advantages of let me give first one advantage of the digital signal, and this advantage is that effects of noise, and interference. Are much reduced. And this is because digital signals are all those of experiment 10, which they call pulses, can be generated and thus restored. So we move on to a simple digital device, which is called a binary device, which I have just shown you an example of. Binary device. A binary digital system. Has got two stable states. stable states. An example of a binary digital device is a manual switch. Manual switch. This one here. And the two states, the two stable states are either on or off. You have no half off or half on. This is not the best we can talk about. Much as you see it as an analog thing where you go and flip, but this is not the best. So this takes us to disadvantages of a manual switch. I tickled you enough. So it depends on how quickly you are putting. So if they say switch on, then I'm like, okay, like some like Alex will do. And hey, switch on. So it is slow. It is slow. And sure. The only thing in that thing is just the contacts for on or off. But look at how it is, the size of it. So it is large. Some people would say bulky. I mean, you may say it is still affordable, but if you compare that switch with the mobile phone, this mobile phone and the current switch I have, it's bulky. And sometimes, have you ever switched on something and it feels like it is not on? It is called, it has a current bounce. It has a current bounce. Pause, what is the problem? The current what should an ideal binary digital device do we say digital or we just go with these two states? If it is ideal, it should be able to give us the two states quickly. So, should be changed. Should be changed instantaneously. Instantaneously. From any of these two states is from one state to another. Two, when you switch it on, it should not consume any of your current. And when you switch it off, it should never consume any. So what should be the impedance when it is off? Infinite or negligible?
Infinite.
Off. And then this is the state. This is the impedance. Off should be
Infinite.
and on
0.
should have infinite impedance. Should have infinite impedance when off, and zero impedance when on. So we have now an example of a binary device, the switch, but also we had a device of a switch which you did not take keen interest about when we were doing the transistors. And that was when a BJT is used as a switch. So when we looked at the load line, and we were looking at when at the tube point, question point, when the transistor was conducting and when it was cut off, if you remember, it was off when I think at the tube point, and that is when it is on. When it is on when, off when IC is equal to 0, that is off, and then it will be on when IC is equal to VCC over RC. So let's look at the BJT, the bipolar junction transistor, as a switch. Which we call an inverter. Is it in D2 or D1? Those who have done D2. Is it in, D1 and D2. Is it in D2 or D1? Oh, you just go in the lab, take my tea, then quickly sneak out with my papers and grab papers, and because I think a bunch of you sneaked up with my papers this last Friday. Many of you. Because when I compared with what I came with what I was going back with, and even if you look at the trash, the ones I was going back with were very few. Very few hand-ins, and compared to how I came with this. Don't steal from me. That camera rolls from the beginning to the end. And even when I'm explaining back at the back and I'm busy with some group, some people look at me and then they pretend like they're I think Wabidi was about to take some, but he remembered. Because he went there and he was like this, he looked at the papers, then it seems he remembered that he just did like this and went away. I review every time when I'm transferring to the computer, I review. So I know all of you who have been going away with my papers. Yes, because I always tally. When you pick, I look at the ones you had in, and you cannot use rough papers which are more than 5. cause me problems. You want to be digital how? And you just submit on the PC or well? No. Some time back, on that oscilloscope, you see there is a slot for a flash. So I adopted, because those PCs the technician use, they are just coming. So I wanted to give I already asked for about each line to have a computer, and then have a several printer. By that time, I think we used to teach a course for 3 years, and then you have to give it up for an Nexus that was whichever. So I was not bad at. I had tried to do that way, so that you don't draw those things, those flowers, those who have done E10, so that you don't suffer with flowers. You just put in the oscilloscope, and then you save, then you go print, and then it will be showing me which oscilloscope printed that, so that you don't print for the generations to come, and then be able to save time. I had that dream, but you know, some of us dream people who are not sleeping. So when you sell their dream, they can't feel what you felt. So you just give up. But that would be the essence. But the Swedish are changing from digital stuff to back to paper, books and the like, because they are losing out on the skills for their children. You find somebody who can't write. But when they go to computer, you see them. But when you say write a cheat, nothing. No, there is a way when you think, when you are thinking. What you write sometimes is what you think. I can give 1 million to one of you who can do this. Who wants to challenge me? You don't even know what I'm doing. But if I want to go to hell, what will you do?
As long as it's money.
I want, if you can do this, I can give you a million. You go with your hand and your foot, and you interchange one of. So this one goes on, and then this. It doesn't matter. You can use the left, this, and then you reverse one of them.
When do you want the challenge?
When do I want the challenge? Now. You want to go, even if you go and practice, it's impossible. The challenge is that when you are writing, and you are doing, when you do, you develop more faculty. When you are typing on phone, the thing comes, you keep sliding to add the word comes, so you never spell anything. Because you never think about the spelling.
Yes, that's right.
Things just come. Things just come. And the reason you are struggling now is that whenever you play computer, you are just choosing. So any word that now you have to write becomes
Even organizing.
because you know everything has been, you just say now, indent left, everything, indent right, everything goes, just fine. So that's the challenge. So the problem is, if you let everything go digital, it's good. But then, this I have showed you becomes now a problem. And that's why, if you looked at your lecturers, whether here, whether in edu, whether in math, they are not this type who grew up, in a comfortable, with everything on. Maybe those who did that are astronauts and whatever, but we normally take the best. So there is a way when you hustle, there is a way you try to make sure that you survive at the end of the day. So, but let's go digital. So we have the BJT, and then we bias the base, and then we have the IC through the RC, then we have the BCC. Am I drawing visible things? Then we have the meter, then we have the art. And I think we can draw the characteristics here. So the load line, to show the load line. And then we have the, and those who are going to code, which one was it? E3. Who with theory? These are IDs. ID is going up. And then you are having the, this is IC versus VCA. And then someone is saying, but they are not changing. IC values are not changing. But you are seeing that your theory, this whole thing is constant. So please go with the theory, because practicals are, we are supposed to be putting the theory into practice. Then we have this as our outline. So if we chose, I think I chose this. We are even doing many for purposes of, but I can still leave the other one there. So here, the transistor is on, and then at this spot here, we do another one. At this spot here, the transistor is off. Then this is VCC. This is VCC over RC. We are varying ID. For different values of ID, we get the characteristic. This is at ID equal to 0. So if we have no current here, then everything would flow. And if everything flows here, then you wouldn't have any output. If you don't have an output, then if you add a LED here to give you the light as indication of the output, you wouldn't have anything there. Then you put on the value, you bias with the ID. So when you put current here, blocks some current which is supposed to come down here. If it blocks it, it flows this side and you get some value. So if you are having an output connected to a motor, a light, a lamp, or any other gadget, then when you have something coming from here that blocks the current, then you get it coming out here. And if you don't have anything here, everything comes and flows down here, and then you get nothing. Yeah, so you can use this as a switch. Always give you a current or no current. You put current here, you blow, then it goes on. You don't put current here, it flows down here, and then this one is off. So you are using your transistor as a switch, but with some good accuracy, more than when you first think, let me switch on. And your rate at which you, so if you are going to do it repetitively, you are switching on, and then you first rub off the sweat, and then you switch on, or you want something disturbs you, so you can. But this one, as long as there is current here, it is off. I mean on. No current, this one comes here, nothing goes there. So for V in less than 0.6 volts, transistor is cut off. Transistor is cut off. If it is less than 0.6, more or less like 0, so nothing is flowing. If it is less than, so everything is here. And whatever is showing that this transistor is on or off is our V output. I'm just going to do this for purposes of formality. So those who have done D1, you know that we have a LED protected by a resistor. And then when we ground it, it can be used as an indicator. So if you have V in less than 0.6 volts, then everything would flow this way, and then nothing would bother to go through here. And that means that you have your transistor cut off. And in that mode, IC would be equal to 0, and then we will have V out being approximately equal to VCC. And for V in greater than 0.6 volts or equal, then the transistor conducts. Transistor conducts. And if it conducts, IC is equal to beta ID, which is equal to approximately VCC over RC, and then V out will be equal to approximately VCC VCE, not VCC, at saturation, which is approximately equal to 0.2 volts. I don't know what's wrong with me today. I came excited. Pick the board. This water cannot clean the duster nicely. Yeah, we leave the board was the standards of so let's look at the clock. this is a periodic. Okay, I know when I talk of clock, some of you will think of the clock on the wall, but the clock is a periodic train of pulses. Periodic train of pulses. And this is, for example, if we drew our V varying with time t, so a train of pulses train of pulses on, off, on, then off, etc. Could have done like 3 or 4. These two are done. This is the time t. This is the vt. And then from the rise time, when it rises again, up to here, is what we call periodic time. So a particle which was here, it will again go back here when you reach this point. And then this is T1. Then this is T2. T is the period. And then frequency is equal to 1 over period. I'm summarizing those of you who go through the ones which are on well, that whole big stuff. There are many words to make you encouraged to read the next step. Here I'm giving a summary of the stuff. The time for 1 over t is what we call a Dewey cycle. So if you are reading and the talk of the Dewey cycle, then you should be able to know what it is. This is T1 over T. Then T1 over T2 is the next space ratio. But these are not practical. These are theoretical pulses, the one we use in the lab. Practical pulses are like, you've done 10.
Yes.
You saw that what should have been a square wave, but then you have some part which is falling in an unnatural way. It's supposed to be falling straight, but it is falling, it is supposed to be this. This, then it falls like this and rises like that. So practically things are different. Since I have rubbed fast clean so that I can rise up, this water should be flowing away. And then I get to have a clean thing. Those of you who don't want to be that, this is my garden. So if I was a farmer, this is my garden. This is why I get a living. If I was a mechanic, this would be the oil I'm acting with. So if you don't want to So the practical pulses are that we have them in a way that they will take some time to rise. So they will take some time to rise. Keep at a value, the own value, and then get off after some time. There are a few things that we shall need to know. So if this was the peak, this is the peak, and this is the 50% of the peak, we shall make some definitions. The first definition is that we shall take 90% of the peak. This is 90%, 0.9 of the peak to peak. So if this is the VT, so this is 0.9% of the, okay, if this is the VT, and then this is the peak value, so this is 0.9 of the peak value, and then we shall also take 10%. Now take the 10%, 0.1 of the peak value, the V roof or V top, whichever you make this mostly in electricity and magnetism. The V roof, the unit direction vector. How did you call it?
Yes.
Unit vector. I can't believe that I can forget these things that I teach. I taught you. So unit direction vector, and this just gives you a direction. It's unity, it's magnitude, it's unity. The only thing it helps you is to show you where the vector is going. And then we have what we call this 90% rise. The time to rise to 90% and the time to rise to 10%. And then also on this other side, we have the peak, we have the 90%, we have the 50%, and we have the 10%. So similarly, we shall have the time for 50%. So for 50%, we shall have this time. And then we shall have the time for the 10%, and then the 9%. And we shall describe them in terms of the rise and the fall. This 0.5, this 50% of the signal of the peak, this time here, the time between here, I don't think this is applied to go up. So this should stop here. So this time, the time between the 50% rise and the 50% fall is what we call the TW. The time between 10% rise and the 9% rise of our signal is what we shall call the T rise, which is T R. So this is the T. Awino. TR. And then during the fall time, the time between the 9% and the 10% is the TF. The fall time between the 10% fall to the 9, so 9% 10% fall is the fall time. And of course this is the time here. I want to repeat it so that you understand the diagram. So one time a professor entered class with a jar full of pebbles. Pebbles, yes, pebbles. Pebbles and gravel, which one is bigger? If you know what I mean. Got pebbles and gravel, which one is bigger? Gravel is like the one on the road, the tarmac road. Then pebbles are really pieces of stone, like the ones they use for building. How do they call those stones? The ones they mix with cement. So when he came with, he asked students, is it food? So his jar was having pebbles. So he asked them, is it food? They said yes. So he put some gravel, he poured in and shook, they all went into space. He said, now is it food? They still said it is food. So he got some sand and poured, shook, the sand disappeared in. Some good amount of sand. Asked, is it now food? He said, no, it is very food. So he got some beer. Okay, he got some liquid. Since the adjunct is done with fasting, I can say beer. I don't take beer personally. I stopped taking beer when I went for holiday after my campus. When I just started working, I went to visit, so we went out. A cousin bought me all sorts of drinks, so I got drunk. So when they reached home, we had 2 homes. So when they brought, first of all, we went to the other cousin. They said, we should organize for you where to sleep and you sleep. They told me, I don't remember, that I told them for us we don't sleep outside our home. So they dropped me at the lower home, but I needed to walk up. So I walked with some drunk fella. Their home was below our home. They were drunkards. So these people who go announcing themselves, me son of so I have come back, don't disturb me. So I hear, I was walking with him speaking English. He had studied up to NTC, so he knew English, that we were conversing in English loudly. So when I reached home, I told my mother that I want to bring balance. So she went to pick a basin, to bring me a basin when I went on the bed until morning. So when I went out of the bed to look for slippers, there was a basin. So I asked her, what the hell is the basin doing under my bed? She said, yeah, you came from down conversing with so and so, that fellow died, may his soul rest in peace. And then when you reached here, you said you want to bring balance, so I brought you a basin. From that day, I said, I was not drinking, but I had started like taking 1 or 2, like if I find people drinking, I shouldn't feel like it is a bad omen. From that day I stopped. How do I walk with someone speaking English in the village? And then I don't know how. So I used beer because the professor wanted to make a point. So he said, your life is like this jar. You choose what to fill it with. You can fill it with pebbles, going to club every time. You can fill it with books, always in the library. Whatever you fill it with, you always have some gaps to fill it with something else. And it is up to you to choose what to fill it with. And if you put in beer first, you will never put a single pebble before the beer overflows. If you fill this with beer first, you can't put anything there. So you have to choose which one to fill it to read first. So this is a practical pulse. With the rise time, with the TW, or what we may call a value, but we shall see what we mean by that time, and then with the fall time. It rises and keeps for some time and comes back, a practical. And the time between when it is 10% to 9%, we call it a rise time. And the time between when it falls from 9% to 10% is what we call a fall time. And then the time between this, we shall see what we call that. And then the time that is between the 50%. And then what else? Those are the key things. So let's.
So nothing from 0 to 10.
Nothing. It doesn't. We don't care so much about it. We care about when it is 10%. Because from 0 to 10, you are within the range. It's like you are within the range of noise. You are still not sure whether this. Remember, I think it is E7. When they tell you increase the input until when the output becomes distorted. You increase for some time, everything is normal. Until when you reach some point, then your impact starts getting felt in the output. This last time. There are silence.
So a good signal, let's say, good pulse then should have what like the time, the TR should be very short or something.
Yes, because now the steeper you get, the shorter you get. The more slanting you get, the more you are expanding it. So, and that is not good. You should be able to have your on, off. So we have the amplitude, our 0.9 of the amplitude, of the peak value or amplitude. Then we have 0.5. Then we have 0.1. Okay, so I forgot that when I was coming with the duster, I was not coming with it when it is fresh, freshly soaked. Only to have the meal soaked and then it wouldn't cause these patches. Okay, so you can see here properly, isn't it? So TR, which is the rise time, is the time for a signal. Is the time for the signal to rise from 10% is the same as 10 over 100, which is 0.1 to 90% of its peak value. Then TF, just for purposes of going step by step, is the time for the signal. So this is fall time. And fall time for a signal to fall is the time for the signal to fall from 90% to 10% of the peak of its peak value. Then finally, not finally, TW, which is the most appreciable size of our pulse, would be the pulse width. The way I have over-explained it, I bring it in a test and still people write for a lot. After taking my time to explain how it comes about. Pulse width, this is time for which its amplitude is better than its amplitude is better than 50% of peak value of its peak value. So once it is more than 50% here, then this is the pulse width. Why do we need these times? These times, that is the rise time, the fall time, and the pulse width time, are used to describe the dynamic behavior, of a logic So what about the propagation delay time? Propagation delay time. Do they still discourage you to write like this from the view? Those of you who are in the view, find out you are writing as if you are writing in a book, as if you are writing forever. I think sometimes the things they taught me in a book on how to teach do not apply. That's the way to tell you to come and first write on board, and then you turn and try to explain. Who has that time? Like I'm supposed to write on board, then I turn. So this one, that's why the syllabus was not getting finished. Chop and explain. People will go and look for more stuff. Not spend it. A geography teacher writes everything, draws maps, and then starts. Even you can't remember how we do the map. It's written now on the board. So the propagation delay time, it would be more helpful to know how much delay is there when you are changing the input to produce an effect in the output. So it is helpful to relate both when you are doing so. It is helpful in the experiment 7. It is helpful to be able to observe how the output is changing as you increase the input. Those of you who haven't done experiment E7, there is a potentiometer here which you can connect to the functional generator. The functional generator is faulty on that experiment. Maybe we shall try another better one. The 20 millivolts peak to peak comes like a miracle when you adjust the knob. When you adjust the knob, it comes like a miracle. You are adjusting like this, then it pops up. When it pops up, stop. Don't bother that button again. Now make sure you are bothering it. We draw this as the potentiometer, but then you have most of them in the lab are like this. You have the cell, this is normally here, this is here, and this is. Then you have the knob. If it is good enough, you use it. If it is not good enough, we normally give you this piece of the transformer for you to be able to adjust. Okay? So once you get a miracle, and then it shows the value on the peak-to-peak value on the scale of the voltage. Don't touch it again. Now adjust the V in here. Adjust the V in here using these methods. It's not my fault that your fathers and your cousins are eating government money when we are supposed to have that money for our brothers. And when they buy you gifts, you are very happy. So I have to tell you how to survive in the lab. But maybe when you graduate, you behave better. And make sure money goes for where it's supposed to go. So once you have, you can adjust this input using this, and you have and the output signal, and then you are supposed to be adjusting this one until when you get the output behaving in a funny way. At distortion, you will find that this other part here almost looks like this. And it's a scheme. You go slowly until when you see that it has become like that, and then you stop. And then you can get the value. This is E7.
But before that, the gamma is so too.
Whatever it becomes,
Where is the distortion?
yeah, whenever it does, whenever it is no longer flowing in a sinusoidal form, then it has been destroyed. That's the problem. As you increase Pin and anything that makes it look not as it should look, then it has been destroyed. So it is helpful to relate the input and the output. The input, so relate, you cannot relate the output timing to the input time. So what is the definition of propagation delay time? The propagation delay time, of a signal path is the time it takes for a change in the input signal, to produce a change. In the output signal. Doesn't make sense really. Okay. So it doesn't relate so well with the part of the how I explained it with E7, because even before distortion, the input would cause a change in the output, even before distortion. So it does not relate that easily, but by definition is when you have a change in the input, but it should be able to cause a change in the output. So we shall draw our input. Then draw the output. So we have PV. This is the input signal. This is the output signal. Then we have VL, this is VH. Then we have 0.5. This is just to, but we have 0.5 here of the VH, half of VH. The output. This is the VL for the output. This is VH not input. And then also the half, 50% of the input. So this is 0.5 of VH minus VL. 0.5, half of this peak to peak, which is VH minus VL. So the time between the 50% of the input to the 50% of the output is TP HL. This is TP LH. And so TP HL, TP this is the propagation in delay time. Propagation delay time when output switches from the output, this one here, when the output switches from high to low, H, high to low. That's why we're saying HL. And then the other one, TPLH. Is the propagation time. When is a delay here. When the output switches from the reverse, switches from low in general, these times can never be equal. So TPHL can never be equal to TPLH. You cannot say when the output is able to switch from low to high that it can be equal to when it is switching from high to low. It's impossible. There is somewhere we looked at this baby here. This is able to describe the behavior of a logic circuit, and this will be our basis of tomorrow's lecture, whereby we shall start on logic gates. So now that we know a few things, we know we can add a pulse, and when we feed this pulse somewhere, it can give us something. For example, when we fed stuff to the transistor, it was able to be on or off. So we can use the same stuff and feed one or more inputs and get one input. Then we shall be able to form a gate. It can be an AND gate, an OR gate, or a NOT gate. That is the basis of the experiment D1 and D2. So after tomorrow, you will be very comfortable with dealing with experiment D1 and after tomorrow, by afternoon, I will be a happy man. I will no longer be hassling with D1 people to explain to them anything. I will do it here and I will be done. I will be just showing you how a breadboard works, but these things of going theoretical will no longer be there. Henceforth, my lab sessions will be the comfortable ones. Any questions? I'm sorry about the board. It's because of it was supposed to have dried a little bit so that I'm able to rub without it putting new marks.
Excuse me.
Yes.
So in that graph, is that what we expect, let's say, in one device or let's say in an element like a PHY looking at the VIN going out from the other side?
Could be an amplifier, could be a clipper, could be you have done the heater. It could be a clipper, could be a clamping circuit. So as long as you are having an input and an output, that time you take to realize a change in the output after trying to change the input is basically the delay time. It's the response time in a nutshell. Stimulus response kind of thing. If you tickle yourself, if they tickle you, how do you feel that stimulus? But in terms of signals, you are looking at when you change, because you are not going to say, I've just pushed in the signal. If you try to change the input, how much time is it taking to give you enough? And for example, D14, when you are doing the timing of the alternating lighting of the LEDs. But, like I say, I am just here to help you and learn. You can learn more than I can. You have a chance to learn more than I can because I can't learn anymore. I learn, but I learn to make sure I explain to you. I can't go there and then I start scratching my head. Then when I'm teaching electricity and mechanism again, how am I going to survive? You get the point? But for you, you can choose now to learn these things and understand them better than I do so that you enjoy the things. So you have liberty to go and research, understand more stuff for your future understanding. In third year, you do a project. So if you want to do a project in electronics, the more you understand these things, the easier your life.